Okay, so now we're going to leave the comfortable and safe confines of static fluids and move on to moving fluids. And today we're going to talk about the almost mythical equation, Bernoulli's equation. And specifically, our goal here is to develop a model that will relate pressures, velocities, and heights under very specific circumstances. Before, we had a model that related pressures and heights, right? Now we're going to add velocities into this mix. We'll talk about what the very specific circumstances means later. First, some vocab. We're going to talk about streamlines. And streamlines are the path or the line in a fluid that is always tangent to the velocity. So what does this mean in practical terms, right? So let's say we have a nozzle here. This is a nozzle. And then with this nozzle, you're going to, if we start right here, the fluid is going to flow and it's going to expand as it goes, right? And the lines you draw that denote this kind of, expand just like that. These lines are always tangent to the velocity, right? They're always tangent to the velocity, so they are streamlines. That assumes, of course, you know the velocity everywhere so that you can calculate the line that is tangent to the flow. And we'll talk about that in more depth of why that's difficult when we go through chapter 4. But for now, it's sufficient to just know that streamlines are basically the lines that show they're tangent to the velocity everywhere. So you get a feel for what the velocity is like everywhere in the flow. Now this nozzle we showed here is what we would call steady flow because the streamlines are all laminar. And with steady flow, particles released from the same positions at different times follow the same streamlines. So let's write that down here. Particles released at different times, but from the same positions follow the same streamlines. Follow the same streamline. So if we release a particle from here, let's say, that particle is going to follow this path just like that. And then if we, at a later time, release another particle from there, it will follow the same path. And that's how we know that is steady flow. The inverse of this, the opposite, is unsteady flow. So if we have a straight channel here and we introduce a obstacle in the flow, and we have the flow move at a high enough speed, you'll learn later that what matters here is actually the Reynolds number, not just the speed. We will talk about the Reynolds number until you're sick of it. But for now, let's just assume that the speed is high enough that we get unsteady flow. And then in which case it'll look like this. Near the top, we might have actually fairly unchanged streamlines, but then there will be flow that rotates and curls and moves chaotically after this obstacle, right? Because this obstacle is going to cause chaotic flow. So that is unsteady flow, because if we were to release a particle at one point from, let's say, this streamline, it might follow the initial one might follow the line that we kind of showed here. A next one we release might follow it for some bit, and then might come back here and then come back out, and it might follow a completely different path, and therefore it is unsteady flow. Notice that the way I've drawn it anyway, the flow is almost rotating at point and tumbling, right? Such flow is called rotational flow. And we will talk about that later in more detail. And one of the reasons why I'm trying to introduce this vocabulary early, even though we're not talking about it in detail now, is one of the things that will get you a job, and one of the things that is a sign of expertise is vocabulary and correctly using words that are have very specific and important meanings in a field, right? So one of the things that will probably most quickly not get you a job, or in other words, get you, if you're on a job interview and you use like Reynolds number incorrectly, almost certainly you won't be hired, right? But if you use it correctly, that's a good sign that you know what you're talking about, right? Whereas if somebody was just, if you, for example, in this problem, and the reason why I'm saying it this way, if you were to talk about just increasing the velocity until you got unsteady flow, that's fine, that's good. But an expert would say, well, you're going to have to increase the Reynolds number until you reach turbulence, right? So the way you talk about it matters. And so I'm hoping to introduce these words early and keep sprinkling them in so that hopefully by the end of the semester, you're much more comfortable with them. Great. So we we talked about a couple of these words. Let's put them into context, right? We talked over here on the left-hand side about laminar flow. Laminar flow. And then we talked about rotational flow. Oops. Rotational flow. And then we talked about turbulent flow. And the important thing for you to remember is that in terms of the way these things are used, we're talking about increasingly chaotic flow. Technically, turbulent flow is rotational, and technically rotational flow is turbulent. But if something is just rotational, you might have regular eddies being shed that would not qualify as necessarily turbulence, but that are rotational. So there is a delineation between these things, but this line here is maybe a little bit blurry at times, right? However, if something is laminar, it is not rotational. And if something is laminar, it is not turbulent. So if you start here on the left-hand side, laminar flow is very orderly. And then as we move to the right, we get increasingly chaotic flow. All right, so to get back on track, we want a model that relates pressures, velocities, and heights. In other words, forces, velocities, and heights. And luckily, we have a model already that kind of starts us along that path, and that is our mascot. Sum of our forces is equal to mass times acceleration. Now, the hard part about this is applying it in a way that makes sense. So if we look let's look at flow around a sphere, laminar flow around a sphere, and try to figure out why this looks hard. So I'm going to draw the streamlines for you for flow around a sphere. And the most important ones are these, the ones that goes and it dead ends on the sphere. So this is like dead center on the sphere. It stops, comes to a complete stop on the sphere. It's called a stagnation point. Again, we'll talk about that in a lot more detail later. And on the other side, we have another stagnation point and another streamline moving away from it, right? And then the streamlines that go around it go just about how you would expect them to, right? So this one kind of clings close to the sphere and then comes like that. And then they increasingly are more gently rounded as you move farther, and they should be symmetric. I'm just not drawing this very well. I'm sorry, guys. You know what? Let's undo that last one. That one was so bad, it does not deserve to stay there. There we go. And then eventually, if we get far enough away, the streamlines are unperturbed by the sphere. So if we were to draw the velocity here, right, we would see that the velocity, let's take this streamline, this top streamline here. We would see that the velocity initially is horizontal, and then it's moving up at an angle, and it's moving horizontal again, and now it's moving down, and now it's moving over here, and that's okay, that's fine. But F equals ma, but this causes a problem because F equals ma in a Cartesian coordinate system requires you to pick a direction, right? Sum all the forces in a direction. We can look at all the directions combined, but then we have three equations that we have to simultaneously solve, right? For all three directions. So the does F equal ma in a Cartesian coordinate system make sense? In other words, is it easy? And the answer to that is no. And the way I would phrase this, remember, if we're doing active learning, this is a great opportunity for you to phrase it in your own way. No, because everything is changing direction. All the time. So instead, we're going to use a streamwise component and a streamwise coordinate system with a streamwise component and a normal component. Okay, so if we draw a few streamlines on the bottom side of this sphere that are meant to mimic, we're gonna just draw them a little bit farther apart. If we were to pick one single point in this streamline, we would see that there is a Vs, which is the streamwise velocity, but there is also a Vn, which is the normal component of the velocity, which points normal to the streamline. And so if we do this, no matter which way the streamline points, let's pick this one right here, we have a streamwise component and a normal component, right? Which is great. That means now we have a consistent coordinate system, even if, at least relative to some kind of datum, our coordinate system is constantly changing its own direction, right? So now you might ask yourself, we're using F equals ma, how does acceleration work here? Well, if we write out our acceleration, so here's our answer. Our acceleration streamwise is equal to dv dt, which is equal to dv ds dt, where s is the direction that the streamline is currently facing, right? So that is a direction, a unit vector, if you will, right? Or, well, it's the change in the, it's not just the direction, it's the change in the streamline. So the change in the streamline relative is actually the velocity at that point. Yeah, so it's not just the direction, it is the change in the position of the streamline as we move along it. So it is the velocity. And so what we end up getting is dv ds times the velocity, right? So that's great. Our normal component of our acceleration, we actually know that already. That's equal to v squared divided by r, where this is the radius of curvature. So we have to do a little bit more work than we might in a Cartesian coordinate system, because we have to find the radius of curvature at every point in order to calculate the normal component of the velocity. And here we have to calculate dv ds. But we have a place to start with acceleration in this coordinate system, and it actually makes things a lot easier in the end if we only worried about changes between points. All right, so let's start our derivation of Bernoulli's equation with our, again, our most fundamental model of mechanical and aerospace engineering, and that is our sum of our forces is equal to mass times acceleration. But we're going to plug in our formula for acceleration in the streamwise direction, which means, by the way, that we're only going to be able to look at forces and pressures and heights in the streamwise direction when we're done. We'll talk a little bit about what kind of restriction that actually is. So we have a some of the forces equation. Now we need a free body diagram, right? And so on the right hand side, I've drawn a fluid element that is a differential fluid element that has a differential length delta n normal to the streamline and a differential length delta s parallel to the streamline. And if we draw the forces on this differential element, if we draw the forces, right, there's going to be a weight mg. There will be pressures on this differential element, and I want you guys to think back to how we did pressures with the differential element with the hydrostatic equation, right? We had a pressure in the middle, and then we talked about the pressure plus a dp d delta S in this case, times a delta S divided by 2, right? We're going to do the exact same thing here. So acting on the top, for example, there is going to be the pressure P in the middle of our differential element plus dp dn, which is the normal direction, times a delta n divided by 2, multiplied by an area. In that case, our area is going to be a delta S, and we didn't denote it in the figure, but let's give our depth into the page a delta Y. So our delta Y is depth into page. Okay, great. So, and in this case too, by the way, we should always draw a coordinate system once we start using coordinates. This is our S direction, and normal is our in hat. Okay, great. So I want you guys to try to fill in the rest of the pressures before I can, right? I mean, it's pretty easy if you can pause the video, but try to fill them in, and then I'll fill them in as well, and we'll compare answers at the end. Okay, you go and pause the video, and then I'll keep going. So we're going to, I'm gonna get the right color. We're going to draw our pressure on the front, which is going to be equal to pressure plus dp ds times delta S over 2 times an area now, which is going to be delta n delta Y. On the back side, we have the same thing, except there's going to be a minus sign because we're moving backwards, right? So we're going to have a P minus delta P, or sorry, dp ds delta S over 2 times an area now, which is just going to be delta n delta Y. And on the bottom, we have another pressure. Let's draw that in real quick. We have a P minus dp dn times delta n divided by 2, all that multiplied by delta S delta Y. And it's finally, we have an mg, but clearly we care about the streamwise direction, right? So let's take the streamwise component of mg, and that's going to be equal to, that's going to be equal, if we call that theta, then we'll be able to break that down later into its components. But we should remember, just off the top of our heads, that delta weight S time is equal to delta weight. This is equal to our delta weight, by the way, our infinitesimal weight of our infinitesimal object times the sine of theta, because we just want that component here opposite the angle, right? Cool. So we have our free body diagram. Let's plug stuff into our some of our forces. So we have some of our forces in the streamwise direction. This is equation 1, so 1 to 2. It's going to be equal to, and let's start going. So we have a P minus delta P delta S over 2 times delta N delta Y minus a P plus dP ds delta S over 2 times delta N delta Y. And then finally, we have a mass component, our weight, right? And that's going to be going in the negative direction, minus rho g sine theta times our volume. the volume of our system, which I'm going to just call for the moment a delta volume. Okay. And it's important to remember that this is actually equal to something here because our stuff is moving. We're no longer in civil engineering territory. So we're going to say that this is equal to rho dV times V dV ds. Cool. We can cancel lots of stuff out of this. So these two pressures cancel out. These two combine into one. And the rest of this is just a volume, ds, dn, dy. We have 2 ds over 2, so that ends up being equal to 1 ds over 2. So when we rewrite this, 2 to 3, we get that some of our forces, S, is equal to dp, ds, dv minus rho g sine theta dv, which is equal to rho delta v dv ds times v. Cool. So we can cancel out our dv, our volumes, our differential volumes from everything, which is great. It's actually the whole reason why we use these differential elements the way we do. And we can now we can convert some stuff. This right-hand side here, which now that we've canceled it out, is equal to rho dv ds times v, is actually equal to rho, it's v over 2 dv squared. Sorry, there's no cross sign there. V squared ds. Actually, I think that velocity is not there. My bad. I don't know why I wrote that. Rho dv squared ds. Great. And we have basically now a differential with respect to s on this side and a differential with respect to s on this side. And we can integrate this. We can say that 0 is equal to the integral of 1 over rho, because we're going to divide this by rho, 1 over rho of dp ds plus the integral of g times, now the sine theta is an issue, but the sine theta is actually equal to, if we look at it, delta z over delta s, right? So if we imagine that this is our delta s, and then we have some kind of z coming down, right? Some delta z, then the ratio of these two lines gives us sine of theta. So we can plug that in here. Let's write it out here though. We say that sine of theta is equal to delta z over delta s. So we're going to plug that in over here, and we get delta z over delta s. And then finally, we get to add in integral of the v squared over ds times 1/2. That's what that was. It was a 1/2. It wasn't what I thought it was. Okay, I didn't read that right. There's a 1/2 right there. Awesome. So if we do these integrals, right, everything is fine because g is normally a constant, so this integral is easy. Rho isn't usually a constant, but if we assume it, if we say explicitly assume rho is equal to a constant, then we can integrate this, and if we do an indefinite integral each time, we get the following. We get pressure divided by rho plus 1/2 v squared plus gc is is equal to a constant. And that constant is the result of that indefinite integration, right? So that's actually pretty easy. And this is our Bernoulli's equation. So let's talk about the rules we have for accurately applying Bernoulli's equation. And we'll also talk about how hard they are to achieve. So number one, the rules. So first rule, steady flow. Second rule, remember, because when we first did this, we had to do along a streamline here. And we don't have any time dependence in this whole equation. So since we don't have any time dependence, all our streamlines have to be the same throughout time, okay? So that's important, steady flow. Two, no viscous forces. In other words, we're pretending like our flow is inviscid, right? It has no viscosity. The reason we're doing that is if we look back at our free body diagram, if we had included viscosity, we would have put a shear stress acting on our fluid that is dependent upon the velocity gradient in that direction. And since we don't have that tau, that we don't have that shear stress, we're neglecting shear stress, which means in order to do this accurately, our fluid must be relatively inviscid. Three, flow must be along a streamline. And typically that means that it cannot be cross fluid boundaries is the main consequence of that. And then four, density has to equal a constant, right? So let's talk about how hard these are to achieve. One, it's actually pretty hard. It's not very common. Finding truly steady flow in nature is, and in stuff we do, is actually pretty rare. It's not in my research. My research is specifically looks at steady flow and really, really small length scales. But in general, most flow we look at doesn't occur at small length scales, so it is unsteady. And most interesting flows are unsteady. So if you think about like flow around a car, driving it, even like slow speeds, even at slow, like 5-10 miles an hour, if you look at the flow around a car, it's going to be unsteady, right? So most interesting flows are unsteady. And that's because for most interesting flows, the Reynolds number is high enough that it is unsteady. Two, no viscous forces. Well, we're working with we're not working with liquid helium. So this is impossible. But remember we said we have a rough model for our shear stress. Our shear stress is equal to mu, our viscosity, times the gradient in our velocity with respect to our distance, right? Change in u, which is the velocity, with respect to a distance. And there's always the distance perpendicular to the velocity, right? So the velocity is going horizontal. We want to see how the velocity is changing vertically. So how can we reduce tau? Reduce tau. And the answer is make our velocity small and make our distances large, right? Velocity small, distances large. Great. Flow along a streamline is relatively difficult to achieve because it needs non-rotational flow. Which is steady flow makes that true, right? If you have steady flow, then you're going to have non-rotational flow. But more specifically, that means we can't use pumps. Or, oops, not that kind of or cross fluid boundaries. And that is kind of hard because we will often have two types of fluid touching each other, like air and water, right? In 4, it's actually not that difficult, right? Not difficult as long as velocity is less than 0.3 c, where c is the speed of sound. So take a step back, and it looks like this is just a tremendously useless equation. It requires steady flow. Sure, none of the flows that we're going to cover in this class as example problems are steady, completely steady. It requires no viscous forces. There's no such thing as an inviscid fluid except for liquid helium, and that's even super cooled liquid helium. Check out some videos of it online. It's pretty amazing. But we don't work with that on a daily basis because we're not at 2 degrees Kelvin. We also need non-rotational flow. Also, flow. It's even harder to achieve than steady flow because that means we also can't cross fluid boundaries. And finally, we are restricted to speeds less than 0.3 degrees, or 0.3 of the speed of sound, and homogeneous fluids, right? It means we can't have mixing and things like that, where the density might vary significantly across the fluid. Those are all, as a whole, very difficult to simultaneously achieve. The fascinating thing about Bernoulli's is it's still remarkably useful in spite of these restrictions, right? And that's why it's so famous, is because even though it has all these restrictions, it works pretty well. Yeah, it works pretty well. And we'll later in the semester we'll make it's not additions to Bernoulli's, although it looks like an addition to Bernoulli's, that will take into account like number 2, viscous forces. Suddenly now we'll be able to add in viscous forces, which is great. We'll be able to add in pumps and things like that, so we no longer have to worry about flow along a streamline. It's not actually Bernoulli's anymore, right? It's conservation of energy in a different way, but we definitely make it much more flexible. Cool. So in our next video, we are going to do an example where we drain a pool because winter is coming, and we're going to see how long we think it takes the pool to drain. And we're going to talk about how accurate the model is in determining that time. And then after that, in class, we're going to talk about our semester-long design project. And we're going to say, we want to know, given a certain strength of our steel, what is the maximum pipe length from pump to jet that we can have, assuming that our V exit is 33 meters per second. That's actually not very fast for a rocket nozzle exit, but we're going to assume that velocity. And we're going to see how it constrains our design, how we can use Bernoulli's to determine some constraints on our design. Cool. All right, so when I see you again, we're going to be talking about draining a pool with a hose.